So yeah, the idea is to, I reread the abstract when you sent it around, and there was like this boring part about the project, so I tried to squeeze it a little bit, so we got a little bit more in the technical part, see if I can manage in the time. So nevertheless, I have a couple of slides of introduction because I don't know the audience. First of all, I have two parts of the introduction. One is the introduction to RISC-V. I don't know, so how many in the room are familiar with RISC-V, or at least you know what it is? Okay, so I can be fast here, okay. And then another one related to the project. So how do we see RISC-V? So how many of you are old enough to have been traveling with this kind of connectors, right? Okay, exactly. So we've been with the Nokia plug and then the Siemens plug, and now we have a standard that is called a universal plug, universal standard bus. Right? It's universal. So all the companies involved in the connector adopted. Here I have a disclaimer. I apologize if you are still an Apple user, but anyhow, at some point you will come and you will understand that having a standard is a benefit for everybody, right? Because I arrived here and they gave me a USB-C connector and everything was working, right? Almost. So, so having standards is good. So which relationship we do have between this funny slide and the RISC-V? Well, the message that we would like, the first message that we want to deliver usually when we introduce RISC-V is that we see it as a standard for instruction sets. In fact, if you think about the history of computer architecture, there have always been, or almost always been, instruction sets that have been proprietary, very common maybe, like Intel in the last 20 years, but not really an open standard that anybody can pick up and make a CPU out of it, say, for free. So the idea of RISC-V is exactly this. So let's define well-defined instruction set architecture. That actually is what represented here. The basic instructions are not so many. You can print it out in an A4 and have it in your room. And define well the instruction set and let everybody use it, okay? And that's actually should be something that has no royalties behind it, right? We just sit down and decide which are the instructions, and then everything else, well, you can make a business out of it. If you do your own implementation, you can still sell it and so on. Another important thing is that probably with these instructions, you can just handle a few of the operation, but maybe you need, we are going to talk about vector extension, right? So RISC-V is an incremental instruction set in the sense that you have different modules that you can, a modular instruction set, RISC-V, versus incremental that is x86, okay? We are going to talk about vectors. Vector is one of the module of the extension that you can enable, right? And here in this table is nice because in the last column you see how many instructions you have in each extension. There are extensions that are only a few instructions, right? The hypervisor adds only 2 instructions, or the user level editor 3 instructions. So there are really small extensions. Nevertheless, you can pick and have your own instruction set for your own CPU that you're going to build. This is, say, as opposite as incremental, like here you have this plot in which on the x-axis you have the years, and here you have the number of x86 instructions that are supported in an x86 CPU. You have this bunch of instructions that are growing and growing, right? Of course, here there is a little bit of marketing as well, right? Because RISC-V, I showed you in the previous slide, is ratified in 2013, while here we have almost 30 years. There is a little bit of, say, less history, so we have less. So we should have this seminar updated in 20 years and see where we are, okay? So, but anyhow, I hope I gave you the messages. So standard, very simple, and with modules or extensions that you can enable if you want to enable certain functionalities, okay? Now, from the business model point of view, this is something that usually from the high level, so if there are people that are more in the industry, they are very energetic with this kind of topics. I just give you a brief pass of which are the features, right? It's open ISA compared to Intel and ARM, they are not open. So if you want to do a CPU based on Intel, probably you cannot. If you want to do based on ARM, you have to pay some royalties, right? And the adoption of the ISA is free in the case of RISC-V. In the case of Intel, if you are AMD, probably you can have some deal. In the case of ARM, once again, you have to pay. It allows development of commercial IP. This is also true for ARM. But the problem, the limitation with ARM is that the development of commercial IP needs to be done in collaboration with ARM, while in the RISC-V part, basically, you can develop and sell any commercial IP. It allows to use to access the extension, and this is the key point since we are in a campus of a university. It allows development of open source IPs, right? And in Europe, we have one of the pioneer group that is the group of Luca Benini in ETH Zurich. They started years ago to develop the first, what is called, it was called the Ariane core, right? So that is open source. You can still download it and put it on your FPGA and do experiments, okay? And actually, we started doing experiment from there also in EPI. Good, so that's a little bit of the high-level introduction. There is one more topic that probably you've heard. You say, oh yeah, RISC-V is like Linux, but for the hardware, right? Linux for the operating system, but on the hardware side. And if you think from the, in a more, not more accurate, much accurate way, probably it's true, but if you look in the details, I would say that is not completely true. Why? Let's analyze how the software flow is usually going, right? You have some software, you have the development of the Linux kernel for Linux, you compile the kernel, you need a compiler, okay, you need people that know the kernels and the configuration of the kernel, and then you use it. Good. On the hardware side, you need the development of a RISC-V IP. That's, I mean, we can assume it's the same complexity of a Linux kernel, I don't know. But then you have to make a tape out of a chip, and then you can use it. So it seems from that point of view, high-level point of view, it seems the same, but there is a tag price, right? That if we discount the hour of the engineers that are working behind, so that this level, the development level has a price, and we assume that it's the same price for software and hardware people. But there is this big price tag that is attached to this make a tape out. So it's definitely not the same thing, okay? So there is a level of complexity, much more money, and a timing process that is completely different, okay? So I would not associate the Linux kernel with RISC-V. Even if both they do have this root of having, something that is open and free for the community. Okay, so take-home message from this high-level point of view. RISC-V define an open source free standard ISA, is simple and modular. It defines sort of, well, not a new business model, more like it extends a little bit the business model that we have today. So we don't have to go with just one provider like in the case of Intel, or just one provider partnership like in the case of ARM. It can be, the implementation can be still open or closed, so you can still do some business based on this. And is likely to work as a standard or a universal ISA. And in the moment in which you are living with bans, wars, and so on, probably could be, it has, well, at least we think we have some value in that sense, okay? Here you have a nice presentation of Kurt Stazanovic 2 years ago, invited talk in supercomputing that is going more into details of this. It's very funny, so it's very interesting. So if you want, when you see this face, the nerdy face, is always because you have something that you can go there and either find a paper or some video and so on. Okay, my second part of the introduction, EPI Processor Initiative. So this is a European project, okay? The objective is basically to enable European technological independence for having hardware based or developed based in Europe, okay? So from the practical point of view, what does it mean? It means we have two lines of work. One is development of a standard CPU based on ARM, that is the left side of this slide. And another one is the development of RISC-V-based accelerators, Okay, so today we're going to focus on this part. And there are, here you have also the name of the partners involved. There are 3 accelerators that are these 3. The EPI accelerator has this very difficult name, that is EPI accelerator EPAC. Okay, good. So that's why we call it EPAC, because it's the EPI accelerator. It has 3 accelerators, RISC-V-based accelerator in it. One is the VEC-tile that we're going to see in the details. Then there is another one developed by CEA, the VRP tile. And then another one developed by Fraunhofer and ETH Zurich, that is the STX tile. These accelerators alone, they are not enough to be operated as a standard CPU, okay? In the sense that you need a memory controller, you need cache levels, you need coherency, you need a network on chip if you want more than one instance of them in the silicon. And also you need the physical implementation to make the actual chip, okay? So all here you have all the other partners involved in the, for example, development of the cache, of the network on chip, of SerDes that we use to interface with the memory, and here Fraunhofer did the physical design and E4 the actual board. Okay. So this is a chip that unfortunately I didn't brought it with me, but it's really physically available. Okay, it has been taped out last year. It's Global Foundry 22 nanometers. If you're familiar with the technology, you know what it means. And it's up and running at BSC. If you are in some of the event, probably you also see some demo that we are showing. Now, for today, we're going to see the details of one of the 3 RISC-V accelerators, that is the VEC-tile. Is the one in which we have the participation, the strongest participation of BSC in the development of the vector processing unit, DPU. Good. What's special in the EPAC? EPAC is the name of the test chip. VEC is the name of one of the 3 accelerators. Okay. So what's special? There are 2 things that are, say, uncommon, or say characteristic. The first one is the Avispado RISC-V core that is made by Semidynamics. The second one is the vector processing unit that is made by the Barcelona Supercomputing Center. How many of you are familiar with the vector computation or vector processing unit? So does anybody understand what I'm talking about? So if I tell you SIMD, AVX 512, everybody knows. Right, so with one instruction, I operate 8 double precision elements. Okay, so that can be assimilated as a vector operation because I'm operating the same instruction over multiple data. Okay, good. That's a very important point. Now, the first special thing is that we have this Avispado core. Is an in-order RISC-V core that has 3 features that are a little bit special. First, it puts Linux. It's useful. Second one is in order and can release several requests of cache lines to the main memory. So if we look at this block diagram, you have the program counter, your instruction, you decode your instruction, and then you have 3 queues: the memory queue, the integer queue, and the floating point vector queue. Okay. So if you go for the memory queue, so that means that you're doing load or store, here you have this module that is Gazillion, it's called Gazillion, is something that they develop internally in Semidynamics, and this module is able to keep up with a lot of requests to and from the memory. Okay, that's the first, the second point so Linux, we have a lot of interaction with the main memory, or say operation in flights. And the third one is we are connected to a very wide, vector processing unit. You have this open vector interface, right? So if you go for this queue, the vector floating point queue, you can connect to the open vector interface. So here we have the second feature of this. So right now we just have a scalar RISC-V core, right? And now we attach a vector processing unit that is a wide SIMD unit. So here you have the comparison of which size of vector we are able to handle, okay? So SIMD, I gave you the example a few moments ago, 8 double precision elements per instruction, okay? ARM with SVE allows up to 2048 bits, so 32 double precision elements per instruction. In our case, in the RISC-V vector accelerator we do have, we operate 256 double precision elements per instruction. So you get the ratio, right? So 32 times wider the vector compared to the Intel. And it's similar, well, actually the same vector size of the NEC Aurora SX accelerator. I don't know if you are familiar with it. So one comment here, in the short vector length, like in the Intel one, you issue an instruction and in one cycle you operate 8 double precision elements, okay? In our case, we cannot operate all the elements in the same cycle, okay? So otherwise we would need 256 functional unit, a football square. A football court of silicon is too expensive, right? So we pipeline the operation on the vector, and we use 8 functional units. So we need 32 cycles to operate a full vector. Okay, so depending the kind of instruction, you have some latency or throughput that is 32 cycles. Good. So now you get the understanding of which is the kind of technology we are using, yeah, right? So we have a standard RISC-V core that can boot Linux, like everything that you are using on your laptop, something like this, different instruction set, and a wide VPU attached. So let's take an example of a code. So here I took the AXP, and here you have this AXP call, in which you have the for loop that is doing the alpha x plus y, okay, and assigning to y. So this is the scalar implementation. If you want to do the Intel x86 implementation with intrinsics, what should you do? Well, you should load first your vector x, then your vector y, and then broadcast the result. Compute the result and then store your result in the memory, okay? So these are the kind of operation that you need to do inside the loop. Before entering the loop, you have to prepare your broadcasting your alpha, your scalar to your 8 double precision elements. So, well, in this case, I'm operating with floats, so we are 16, a single precision element. Okay, now what happens if this n, that is the size of my vector, is not a multiple of 8? Well, I have these tails, right? So I have to handle the remaining elements of the vector in a separate way. So here is one feature that has the RISC-V vector extension that is called variable vector length or vector length agnosticism. And let's have a look at the code, right? So first of all, well, here we have the broadcasting, okay? These are the built-ins we have in EPI, but you can assume they are the same. So here we have the broadcasting. Then we enter the for loop. And the first thing we do in the iteration of the for loop, we ask with one instruction to set the vector length. And we set this variable that is called granted vector length with the value that is returned by the hardware. Okay, so it's the hardware that is telling us which is the vector length that we can use. We can ask for 1 megabyte. He will return us the value that he has available. I mean the hardware has available. Okay. And then we operate, so we do the body of the loop, and then we go back. Okay, and in this way, we don't need to handle tails, right? Because if we always ask the remaining number of elements that we have in our loop, and this data is available because we are looping, we are counting how many elements we do have, we can always know where we are in our loop. So we don't need to take into account vector tails of our loop, okay? So that's one thing that is different. Say, if you ask me, what's the difference with the AVX 512? Well, this is one of the biggest difference. We have I have backup slides with several other architectural differences if you want, and if we have time later, we can look into that. If you want to play with this, we have this compiler explorer with the compiler, our compiler, so you can put there your code and try to play and see what's the output, okay? Now, how do we program this? we have actual hardware, okay, available. So usually what we promote is the auto-vectorization. We develop a compiler that is based on LLVM. So we provide you with a compiler that is able to auto-vectorize codes, not all codes, but it has the function of auto-vectorizing. If you want, you can annotate your code with the Pragma YP-SIMD, that we call it guided vectorization. Otherwise, you can use C and C++ and Fortran. Here I forgot, also Fortran built-ins, so use intrinsics. Or, well, you see the level of happiness of the programmer here. Or you can use assembler. I mean, you're getting harder and harder. There is one red line here. So in the moment in which you go lower than this line, your code is not portable anymore. So be careful what you do, right? If you need to execute your code in different machines, don't get here. But say all these levels are available. Now, how do we use it? Well, we have the hardware, we have an operating system booting, we have a compiler, we have a scheduler, Slurm is up and running, we have libraries, we have a programming model, or say we support OpenMP and MPI. And basically, if you have a parallel application, you can come and try, compile, and run. Okay. If everything goes well, you have a binary with vector instructions, and you can execute and get some speed up. Later, I have an example of one fluid dynamics code that we studied, so we can see the kind of painful that you have to go through, of pain that you have to go through if you want to pass through that. Take-home message here. From the EPI point of view, we are developing R-based CPU, RISC-V-based accelerators. We focus on the vector accelerator, and that can be self-hosted. So we operate it like a standard CPU, because remember I told you the core is able to boot Linux, so we boot Linux. It supports variable vector length, the thing that I show you of the tails of the loops, is vector length agnostic, and use long vectors, 256 double precision elements. Okay, so probably your algorithm or your application needs to be prepared for that. So now we jump into the topic that is what we really do on our daily basis in our team at BSc. So we call it software development vehicle. And it's basically a set of tools and hardware and software tools that allow people to use this kind of, test this kind of architecture, okay? So in principle, if you want, when we finish this seminar, we can give you an account and you can start playing with this, okay? So what do we have and why do we do this job? Because we have this. In EPI, we really do the tape out of chips, right? So you have these hardware development cycles that you have the hardware people that are on the blackboard defining the architecture and then do the RTL implementation, the RTL verification, and the month goes by and software people are just sitting there waiting for a chip to do something, right? So what we try to do is to move the moment in which the software people can do something on the left, or say, on the left as possible, right? To be able to experiment with the architecture. So with the simulator, you can just operate at, say, few hundred or thousand, or if you're lucky, million of operation, but not so many. And so here is what we define software development vehicles, okay? So if you are the user, pick your color, you log in into an ECA, we call it, well, it's an x86 standard server, okay? And you will end up in a network that is our network where we have all our system. And you can have access 3 types of resources. The first one is commercial RISC-V scalar nodes, things that you can buy in MediaMarkt, or say, things that are commercial. And so you can log in there, compile, and test your code. No vectors, okay? So there you can go and see if your code is running, or it has, for example, some dependencies on intrinsics of Intel or something like this. Then the second step is running with an emulator. So you start enabling auto-vectorization, you get a binary with vector instruction, and you emulate on using QEMU plus a plugin that we develop that gives you some insight statistics. And the third step is the RISC-V prototype vector. So you run on the real hardware. Okay. So these are the three steps that we suggest. So you come with your C or Fortran code. You compile it, you run it on the Scala. You see the blue path, okay? If you enable the auto-vectorization, your binary will have vector instruction on it, so you jump on the green part, and you can emulate it with QEMU and Rave. If you have the same binary, can also run on the hardware, the actual hardware of the project. Okay, so when I say the actual hardware, I mean the test chip that I showed you before in the image and an FPGA implementation that is the brother. So they are basically the same thing at different frequency. Okay. Here we use standard tools, LLVM, QEMU, PAPI, and ChipScope for internal logic analyzing. And here is I just put this slide one view of all the things that you can visualize or understand about your code, right? First of all, you can instrument your code regions. And basically on the x-axis here, you have simulated instruction or time, basically. And you can see code of your regions that you are interested in. Then in this code, in these regions, you can understand where the scalar and the vector instruction are executed. So here we are able to emulate the vector instruction, and you get colors where you have vector instruction. Okay? Colors means which kind of instruction. So you not only know how many, but you can also know which type of vector instruction, and also you can know which is the vector length that these instructions are using. Right? Because if we have vectors of 256 elements, but we are constantly using only 4 elements, well, we are underutilizing our resources, okay? Good, so that's the kind of infrastructure, so hardware, we need a little bit of hardware support and software support for enabling people that are coming with their software to test this platform. So here is always the same 3 steps as before. The only point here is the clearance semaphore. The third step, so running on the actual FPGA somehow has less clearance. You have to be in contact first with the project so it's not freely available for everybody. But all the rest is really available. So take home message. While the RTL is becoming available, that is a long process, we want to make software people able to run on our platform, test their platform, give feedback, adapt their code, and so on. And so for this, we started this software development vehicle infrastructure. And the idea of the software development vehicles is doing 3 things. First of all, if we see some bug in the hardware, we can go back to the RTL guys and say, hey, you said that a fuse multiply hat should take 32 cycles, and I see 38. You have 6 more cycles, and I don't know where they come from. This is an example that actually happened at the very beginning, okay? So imagine that you make saving 6 cycles over 38, sorry, in all the FMA that you do in the world in one processor. It's a lot of cycles, okay? So this is the first point. So you can fix bug or say implementation, suboptimal implementation in the hardware. Second point, you can collaborate with the compiler team. That is actually, the head of the compiler team is my office mate. So it's really a close interaction. Third point, you can interact with the people that are developing or using the scientific application to prepare them for this architecture. And actually, this morning we had a meeting with the people of Alberla because we have this kind of collaboration under another project that is not EPI, okay? So these are the 3 objectives of this kind of infrastructure. And here, in the last 15 minutes, I have the example of a fluid dynamics code that we ported to our infrastructure. Okay. Actually, in reality, I do have also benchmarking of our architecture, but let's see if I can fit both of them. So the code is called Alya. Let's look at the images that are clearer than a lot of words. So on the x-axis, you have time. On the y-axis here, you have MPI processing. Here, the important point are the colors. Okay. You see that you have a say, repetitive pattern. Okay, this is what we call one-time step of computation in this fluid dynamics code, whatever it is. And the blue part is called element assembly. Okay, and is one kernel that is, as you can see, critical in the execution time. Okay, and the developers of Alya decided to implement this code with a parameter that is a sort of blocking. Okay, so unfortunately they call it vector size. Okay, it's the worst name that they could give for somebody that should explain now after introducing all the vector stuff. So vector size from now on is not the vector length. Okay, vector length is the architecture parameter. Vector size is like a block size in when you do blocking in a matrix multiplication. Okay, so take this in your mind. Good. So we took the mini app of the blue part of the element assembly, and we divided it in phases. We find basically in loops, all the loops that we have inside the code. And we started with our tools without using intrinsics, because we know that this code is running on Intel, on other architecture, okay? So we don't want to compromise portability. The first step is run, I'm the blue box as before, so run on the commercial RISC-V platform, okay? So here in this table you have the different phases, and here the percentage of cycles that are spent in each phases, okay? So in the color code, you immediately see the phase 6 is the one that is taking more cycles, so more time. And then we also understood that there is a, say, direct connection between compute intensive and number of cycles, whatever. So, and another important point here is that if you change the vector size, so if you change the blocking of this problem, actually the total cycles are not changing much, okay? So if you are running Scala, you don't get much effect, you are not much affected by this blocking, okay? But if you enable the auto-vectorization, and now I'm doing a little bit of a trick, so I jump in the future, okay? Imagine that we take the binary and we go directly to the hardware and we measure the total cycles, just enabling vectorization. Here you have on the y-axis the total cycles, and on the x-axis your block size. And you see that your the block size, or vector size as the developer call it, is really affecting how the performance is going, okay? So in reality, the developers, they really got something that's organized the data such that is vector friendly, okay? And this is just enabling the auto-vectorization on this kernel of the application, nothing else, okay? But be aware that here I'm a little bit cheating, right? Because I jumped directly to the end. Now, the second step is the emulation using Drave, the QEMU plugin. Here you can see the percentage of vector instructions that are present in each phase, okay? We have a color code. Green is about 30%, and 0 is red, okay? And if we look at the analysis of the type of vector instruction in this plot, you have clearly the feeling of how that there are a lot of memory instructions. So brown here, I don't know if you can see it. So brown is memory instruction, the dark brown. Okay, so 70% are vector memory instruction. And you can already understand something, right? That, for example, that phase 7 seems to be in good shape. Phase 1, 2, and 3, nah, not so much. What about phase 6? Phase 6 was the one of the taking a long time in the Scala part, okay? We see here that, please be aware that I'm changing now. I'm showing you the percentage of vector cycles, okay? Not the vector instruction. So now I'm showing you how much time I'm spending executing vector instruction compared to the total execution time, okay? So you see that here we have about 20% of the phase 6 have about 20% of the vector instruction, and we are able to cover between 85 and 90% of the execution time. So you don't need much instruction, vector instruction, to have a lot of benefit, say. This is true because we have such an unbalanced architecture, large vector and small, say, in-order core, okay? High CPI, we are computing several elements per instruction. This is good. High CPI, you see it here, right? So vector CPI, clock per instruction, okay? if this is going towards 32 is our magic number. Why? Because I told you we need 32 cycles to process one vector, right? So if you have 200 cycles for instruction, it's bad. If you have 40, well, it's okay. You can consider that you have some tails here and there, so you have to reduce your vector length. Here you have the average vector length. This is also a good number, right? You're increasing your vector size, so the block size parameter, you get basically a vector length that is corresponding to the vector size. And it stays there at 256. So these are the kind of things that we can study, say, on a code and optimize. Now, let's see the phases because now I was starting from the good news, right? So the phases that are working well. Now, what about phase 1, 2, and 8 that have 0 vector instruction? So let's start looking into phase 2. Why phase 2? Because it's the one that is in percentage taking more time. Is this phase. So first of all, we detect that the compiler is telling us that there is an unsafe assumption because of this vector dim. We look into the code, vector dim, it seems that is something that is fixed. It doesn't change at runtime, and actually it's just something that has been left there and can be set at the same size of vector size. Okay, so we basically found out that this was a safe assumption of the compiler. When we fix this, we should be able to get vectorization. Great. So we go back, we measure the total cycles, and the solid red gives you the total cycle with the wrong parameter, and the dashed red is with the fixed parameter, and you get slower instead of faster. You see, the bars are constantly higher, right? So we get vector instruction, but we are going slower. Why? Well, we look into the data, and the vector length, we discovered that the vector length is lower than 256. It's actually, I think it was 4, something like this. So we go back to the code, we look into the structure of the loops, and we see that the loops are structured like this. There is an external loop and there's an internal loop, and this internal loop has a strong limitation from, I think, 0 to 3 or something like this. Okay, so the compiler is trying to auto-vectorize the inner loop. The inner loop has this hard constraint, so we get most of our vector wasted because of this. So we swap the loops, and we actually get this result. Okay, so these are the kind of things that you have to understand and to change in your code in order to get, now the new results are these squared bars, okay? That is what you expect. So these are the kind of things that you can do in codes to prepare, to make your code more vector friendly. Now, we applied this, and this is before the optimization. This is the vector 2, sorry, the phase 2, how much in percentage was taking, and here is after the optimization. You see that basically it stays constant and is very little now. Good, so we did all of this with all the other phases, and here is the final result, basically, the overall speed up of the application. So the scalar execution is the light red, and after all the optimization you have the dark red. Okay, so here you have the actual speed up after all these tips and tricks into the code, okay? Now, the real point here is not, you can tell me, well, speed up of 7 is too much, is too little, much of effort is not enough, I don't know, but if I use CUDA, I have, anyhow. Here, the good message is that I take the very same code, and I go back to Mare Nostrum, is our supercomputer in Barcelona Supercomputing Center, and I compile with the Intel compiler, and I run it, and I discover that I have a speed up compared to the Intel version as well. So what I'm saying is that we are enabling vectorization in RISC-V, but since the code is portable, everything that we are doing on the code is also benefiting the rest of the compiler. And we also did a test on the NEC Aurora. So you see that the speed up is not much, it's not as large as in the RISC-V, but you always have a speed up that is positive here. Okay, so that's the kind of work that we are doing on real application. Then we have some work also with intrinsics on libraries, because of course you want to prepare some linear algebra libraries, and that's the kind of preparation of the system software that we are doing. So take-home message: we are leveraging all the infrastructure that I showed you before for running complex CFD codes like Alya, but we are doing similar thing with Valberla right now. Maybe in Christmas next year I can present the update with Valberla, maybe. And the vectorization technique improves the performance on EPAC VEC, because we show you 7 point something x speed up, but they are portable. We are doing similar study with different center of excellence. And here you have the paper, and also you have in the room the author of the paper. So if you want to blame somebody, go to him. That is the study of the Alya code. Now, I just have 15 minutes, and I have one section dedicated to micro benchmarking, okay? I just jumped to 3 slides that are 3 plots, okay? Because we did a comparison between the EPAC VEC and some RISC-V commercial platform, and some Intel x86 Sapphire Rapids and NVIDIA GPU H100. Okay, so very state of the art. We took 4 kernels, AXP, GEM, so matrix multiplication, FFT, and the conjugate gradient. We took the best performing version of this code. Don't worry about, I mean, it can be auto-vectorized, it can be with intrinsics, whatever, okay? And we ran it on all these platforms, okay? And here we report the performance in flop per cycles, and in the following slide we have the percentage of the peak. So percentage of the peak, of the theoretical peak of the machine, okay? So if we look at the flop per cycles, on the x-axis usually you have the size of the problem that you are computing, okay? On the y-axis you always have the flop per cycles, and there are interesting observations here, okay? We could stay here. Probably 1 hour is very short for this, but I wanted just to show you, because you know the kind of study that we are doing. Later we can share the slide. You can go there, look into the lines, and understand the kind of things that we are doing. There are highlights, like for example, in the case of FFT or conjugate gradient, in which the EPAC basically behaves like, so delivers a similar performance like an Intel one, with half of the functional unit, okay? And the other funny things is, if you look at the green, now here, sorry, I was looking the blue line, that is Intel, because blue is the color of Intel, and the yellow one, the one of EPAC, right? And also here, basically, these are the points that I was showing. Then there is the other point, that we are taking the timing of the H100, the largest GPU that we have in the market, probably, with and without taking into account the memory, the host-to-device transactions, and taking into account them. Okay, so if you only take the kernel, you have this kind of line. If you take the flop per cycles, if you do not take into account the transfers, you have this line. So you see the impact for example, in the GEM. Look the impact of the host device model you have on a matrix multiplication. This is pretty huge. Now, another comment is about the efficiency. So how much percentage of the peak you are taking, you are basically squeezing out from your architecture, right? And here another point is, well, EPAC is doing pretty good, depending if you see in the implementation of FPGA or the test chip here. We lose too much time if I explain the difference. But anyhow, look into yellow and brown. Yellow and brown are almost always in the highest part of this plot, right? And another say, comment is, look at the low efficiency of the GPU. So GPUs are really powerful, but we are squeezing very little out of them. So we should squeeze more. Or jump to the vector processing unit, I don't know. Anyhow, this was the thing that I wanted to show. And then there is always the question about power consumption, so I leave the plot for later when somebody will ask, which is the power efficiency of the, so I will explain this in the questions. Take-home messages here. We did an evaluation with real computational kernels that is different from the real scientific code that I did before. This is definitely not portable. It was really tuning and so on. It took a lot of hours. Here you have the tables with the hours with all we need in all the machines. And it shows us excellent stability, say on our side, so it was not breaking every 2 seconds. It evaluates the standard HPC tool, so there is nothing weird here. It's Linux, compiler, and libraries that you use on a daily basis. And and here there is still the mention of Walberla. So the lesson learned is that all the tools that I showed you before, the colorful timeline and so on, are really important to understand the insight in all this architecture. Okay, so microscopic, execution level, and also internal to the chip. And here we have this comic that is in Spanish. It's like the kid that says, you see, I didn't want to take the shower and I'm not going to take the shower. And the mom is basically dragging him to the shower, right? So here, basically, I spent 1 hour to try to convince you that doing vector computation is good, but I'm sure somebody will drag me to the shower, but at least I tried with all my goodwill, okay? So that's the message. Here I leave a page with the references of study and measurement and papers that we did on these platforms. And that's it. I leave time, 10 minutes for the questions. Thank you very much.
I have a question about the whole concept of long vector architecture.
Sure.
So are there registers that are as long as the vector length? Does the CPU, does the instruction set have registers?
Yes, it's like a standard register file that you have in a CPU, but with the size of your vector. So
256.
256 double precision. So 16 kilobits every register, multiplied by 32, I think. We have 40 because we have renaming.
Yeah.
So
that's a lot of...
it's a little bit of area, yes. If you look into the area, yes, it's a bit of investment.
Yeah. Are there caches for the vector side?
Yes, we do have a level 1 cache that is, a level 1 and a level 2, and then main memory. And the level 1 is bypassed by the vector instruction, because basically, if you have a vector miss and you go to the L1, you basically wipe away the whole L1, and the poor scalar core is crying. So basically, we just go to the L2.
Yeah. Okay, so all the reuse has to happen out of the registers, or you run out of level 2 cache. I run out of the level, not out of, or you use the level 2 cache for caching purposes.
We use the level L2 for caches, yes.
I've been asking that because I'm actually pretty familiar with the Alya code.
Okay.
We've been working with this exact function like very extensively in the last time. And so what we found is like that there's a ton of intermediate values, and these allocated vectors that are very vector friendly. I think I've calculated something like 2 to 3 kilobytes of intermediate data per element. So if you use 256 elements, a vector length, that's 256 times 2 to 3. That's like half a megabyte of intermediate data that you ideally want to hold somewhere. I found that for CPUs, it's kind of fine. If you use a vector length like 16, or for example, then you get something that fits into the level 1 cache, and then yes, you load the data in and out of the level 1 cache very often, but that's kind of fine. But it's very bad on GPUs, because there you need like longer, like the amount of cache you have per vector length lane is less, so you load everything out of DRAM, and then it becomes a very DRAM limited function, whereas on CPU it's compute bound.
Okay.
And we fixed this by removing these global intermediates, like these vectorized intermediates, and making them scalar, making them scalar again, and also specializing a little bit, removing a lot of that stuff. We made stuff like pNode, which is always 4 for tetrahedra, made it a constant and specialized for tetrahedra, for example.
Sure.
And we could remove a lot of the intermediates, and then it runs like 50 times faster on the GPU. So this amount of, I feel that with this long vector approach, there's a lot of, you need to run a lot out of probably either level 2 cache or even DRAM, and that feels somewhat inefficient to me. That's why I wonder whether the long vector length, whether they don't generally suffer from less locality, more intermediate data, and whether that isn't inefficient. I mean, you have a lot of memory instructions on this one slide.
Yeah, but that memory instruction were because we were using structures that were this compact representation of Fortran that you write an operation in just one line, and basically the compiler
kind of confuses the compilers.
Yeah, exactly.
They could keep a lot more stuff in registers, but they don't.
Exactly. So that's tons of memory instruction basically disappeared in the moment in which we expanded that way of writing. Yeah.
How large is the level 2 cache?
1 megabyte.
Okay, so that would just fit the data structures of Alya.
Yeah.
There's a question in the chat, very technical. I have a question on the cost of computing the number of active elements via VSET-VL. In your examples, VSET-VL is executed in the loop. How expensive is this? My experience with ARM SVE is that it's typically better to compute the number of full iterations, use a fixed true predicate for these full iterations, and only compute a predicate for the tail to limit the number of active vector elements.
True. Got it. I don't have direct experience with the SVE, but I can guess because why the person is saying that it's better to pre-compute it, because in SVE, if I remember, you operate with masks, while here is really limiting the size of your vector that is given. Going back to the question. How much expensive it is very little expensive. I think that is 1 or 2 cycles.
So compared to a vector arithmetic instruction is negligible.
Exactly.
1, 2.
Also, you have to remember, this also is something that sometimes slips from our minds, that the vector is huge. So the number of iterations that you do are not so many, right? Because you reduce a lot the looping and looping. So that instruction is actually not called as much as in an Intel or an SVE implementation. Anyhow, really, it's really 1 or 2 cycles. It's not so impacting as one can imagine.
I think it's a very valid argument that the vector length is so huge that you take 32 cycles to do a vector add, for example. A lot of other stuff can be hidden behind that.
True. Yes. From the room.
I actually have 2 questions. One is, when you're parsing, like you showed how the vector is not processed as a whole, but step by step, I think in the facts of 8 entries.
Yes.
How does this combine with pipelining? So do you have hardware pipeline in your vector engine, and if a vector is partially evaluated, can those, like the first pack of results already be reused in the next instruction, so that
I think you are asking this. Tell me if it's true, right? We are vector loading V1, multiplying V1 by V2 and putting the result in V3, and then using V3 for doing a vector add with V4, right?
That's the precisely the idea.
Exactly. So the answer is yes. Instead of doing this, load, mul, add, we can do this. So as long as we have the first bunch of data, that probably will be the first line of cache, because we operate with cache lines, we can start. Mark is looking at me like...
Executing a mul and an add at the same time?
No, sorry. Yeah, you're right. This is general chaining. Sorry. This is general chaining in the book, okay? What we can do, we can overlap the violet and the green. Not the green and the add, sorry, because we don't have an add functional unit for doing it. Sorry, you're right.
So that's just one vector on...
Yes. Yes.
So you will still have to complete the evaluation of the entire multiplication, all vector elements?
Totally, yes. Sorry. Thank you, Mark, because this was a slide for introducing the concept of chaining without taking into account our architecture. So.
Yeah, because I was also usually you want to hide computation by overlapping it, by using several parallel ALUs and pipelining stuff. So basically you don't do that, but instead rely define very large vector lengths.
Exactly.
Can you compare the throughput you're getting from this strategy versus pipelining?
Which would be an example of pipelining that you would consider? So maybe I can show you the data.
Actually, I'm putting this all together.
Yeah. No, don't worry. We can follow up later.
Computations are pipelined. They're pipelined through the eight units that you have.
Links,
it's just hidden behind this one instruction that does it all from a user perspective. It's very reminiscent of old school vector computers we had in the 80s. And the pipelining does happen. The real question is, how well does this work in practice? I mean, in the true implementation later on silicon, you may be able to have more than one arithmetic logic unit. So you may be able to do the multiply and add in this pipeline fashion.
Sure. Well, right now we can only overlap the channel that is, so the operation that are going to the memory and the one that is going to the functional units. But if you want another way of seeing all this, if it helps for your under the shower for tomorrow morning, is imagine that the vector instruction are like kernels in GPUs computing, right? So you have your scalar flow of your program, and at some point your scalar flow has a bunch of work that is taking a lot of cycles, and you throw it to the vector unit, exactly like you throw it to the GPU. The difference is that when you throw it to the GPU, you have to contaminate your programming, saying, okay, put this data there, put this computation there, execute it, take it back, while in this case is all inside the same binary, all inside the same flow. This is, say, another way of seeing, because you are instantiating a lot of work every time that you instantiate one vector instruction. And you can hide a lot of smaller scalar instruction underneath.
This was actually something else I was learning about, because you said that you had an in-order scalar in the CPU, and in my experience, you want to keep your vector units busy, so you have to keep providing them with data. And a classical system would need a good, for instance, a good out-of-order engine to do that, which you don't have. But having those extremely low vector units is sufficient, such that the control unit can keep providing them with input so they never idle.
Yeah,
is that correct?
It's correct, but I think that we are mixing where to put the stress. So in your sentence, you said you want a lot of data coming in, right? So the guy that is doing this work is this guy that is filling us with a lot of data. The front end of the CPU is pretty relaxed because he does some work, he finds some vector instruction, he gives it to the vector unit, then he's sitting there waiting. Probably he can move on a little bit, but not much. The really blocking part is the request to the memory that is kept up by this guy that is sending back and forth requests with vector load and vector store.
It's getting clearer to me now, because your instruction scheduling front end has a lot fewer instructions, because every instruction calculates so much.
Correct.
So much data, so you don't have a pressure on the decoder and the scheduling to provide instructions.
Yes. This doesn't mean that we cannot take advantage of a good out of order here. In fact, in the next iteration that we're going to tap out next year, there will be a core with out of order. So I'm not saying out of order is useless, just do this. I'm saying that in this stage in which we explore this design point that is so extreme, you don't suffer much of what you are saying, because basically you have so much work to do that the front end is way more relaxed than an Intel is on holiday with a beer. Front end, relaxed front end.
And then I had one other line of questioning, which is about the compiler.
Sure.
So you said you were working with LLVM.
Yes.
You have been developing, if I understand correctly, your own compiler based on LLVM. Is that right?
No. Is mostly streamline LLVM, the thing that you can download on the web of LLVM, plugged with some auto-vectorization feature that we develop inside our center. But I mean, to let you understand, The compiler BSc team is taking part in the LLVM calls with the ARP team, the NVIDIA team, the Google team, and so on. So it's really something that is coordinated, and I think we have a merge every week or something like this with the main. So it's not really a branch that is going full crazy.
It's not dependent on your vendor compiler, but one can use Clang and get to the same level of performance.
You can use Clang and have some vector instructions, probably not the same level of performance. You can even use GCC and having vector instructions, no problem. Probably it's not so well optimized because here we have some scheduling things. For example, we know that we can overlap memory and arithmetic. So when you put -m EPI, that is our flag, well, there you are giving a little bit of help to our implementation compared to the standard one that you have in the...
Are these changes meant to end up in mainline LLVM?
I think so.
Okay, but so it means at some point when it's all ready, you can just use the flag.
Yes, that's the idea. That's the idea.
Was another worry I had because it's nice to have develop a compiler very specific for this architecture. But experience with such vendor compilers which they were then lacking behind very strongly on the side of language features, C++, for instance, that you couldn't use C++ 20 for instance in these compilers.
No, that's the idea of not to repeat that experience. You've been traumatized by the Fujitsu compiler or what?
Exactly.
Okay, let's.
One question from the chat, something we all want to know. Do you have a roadmap or estimate on when a production-ready RISC-V chip suitable for HPC becomes available?
So the short answer is no. I don't have idea. What I see, I'm old enough to have witnessed 2 iterations of this thing. So I came, I went to BSc in 2012, 2013 to jump into the Mont Blanc project. Mont Blanc was doing similar thing with ARM. So we were pushing ARM architecture into HPC. Okay, so if I do the math, when was Fugaku the first time in top 500? 20, 22?
20.
20, good.
19 and 20, but I think
Okay.
19.
So 10 years, more or less, to get to the top 500, okay? So
Thunder X2, which is a little...
Yes, there was Thunder X2, is true, but I also have to admit that they had a strong company behind that was ARM, that was pushing a lot of money involved, blah, blah, blah. So this time, 10 years, count 10 years. So, I mean, I'm now feeling the same things that I was feeling in 2013 when I started with my prototypes in the lab and so on. So we are more or less there, okay? We were testing with Android development kits at that time. So now we are using these funny cards. So what I'm saying is you need a champion. And champion can be either somebody that believes and puts a lot of money or a lot of investments, or a crisis. Or we have the goodwill of people that are interested and so on, but then it's slow. Now I'm removing all the hats of, and just speaking as Filippo. So this is my feeling. Maybe tomorrow we have an announcement of a beautiful server chip, but that's a little bit my feeling. This doesn't mean that we have to throw away and stop working on this. Is throw away the effort, I mean. The European effort is very useful. We are learning a lot. Probably we will have Alpha Rack at some point of this kind of technology in one of the installation, I don't know, in BSc or ULIC, or I can expect that at some point we can reach that kind. So this is 22 nanometers. The next one is planned to be 12 nanometers. It's a tape out with 8 cores and will be next year. Usually you need 3 iterations to get something meaningful. So maybe the next one. So probably I was vague enough. But I mean, I answer with my experience. That's the only thing that I can share, right?
There was already quite some discussion on the variable vector instruction form.
Sure.
That's useful to want the loop after the loop. You support also in hardware different numbers of vector lines that the binary is compatible to exploit. For instance, if you have 4 links and 8 lanes, and the same binary can utilize the different amounts of vector links.
This.
You have to recompile the source code of all this to utilize different types of vector units.
No, that's the point of having this kind of approach, that the same binary can use the different kind of, and this is what makes the life of these two guys more difficult, because if they want to static analyzing a binary and they don't know which hardware is underneath, they have some difficulties because they don't know which kind of, how many lanes we do have available.
Exactly, that's the idea of the extension in the standard, but I got a little bit confused with your
No, it's
from source code to assembly.
Sure.
Okay, then I have a second question. You mentioned these two development teams, hardware and software, and at some point of time you have the RTL description and start to develop the QEMU simulator.
Yeah.
How does it work actually? Does somebody study the registered transfer level description and tries to implement all these features in the simulator, or do you have some means like architecture description languages which are converted from the architectural description into a simulator and also be used for retarget to the compiler?
So in the pure simulator, people are using the Gem 5 simulator. That is basically a software infrastructure that already supports some of the module. Maybe somebody knows better than me. It's a team that is not our team. Say, it's another team in BSc closer to the RTL team. I think that yes, you need some knowledge that is flowing from the architecture team to the simulator team. Yeah, that's.
Question goes into the direction whether this is automated or semi-automated.
No, this.
You just throw the model.
No. This is something that really happened. Then there is the emulator that is not the simulator, and that is based on QEMU, and that is something that is basically we can sit down and install it now here and have a QEMU instance that is able to run RISC-V binaries. And that is something that we did in our team, because the point is you just take the QEMU infrastructure and you plug in and you say, hey, wait a second, when you decode the instruction, if you find the vector instruction, you just have to plug there your routines and say what you want to do when you have a vector instruction, right? So collect your data and so on. But all the rest of the infrastructure of emulation is there because the community is already developing QEMU. Okay, so these are the two paths, but they are really going to different ways, right? If you want to explore which needs to be your best cache size, like you have to use probably a simulator. If you want, with QEMU, you can do, say, other kind of studies.
I actually seen the prototype back in the EuroHP Summit earlier this year. Rabbi.
Good.
Yeah.
Thank you for visiting us.
Yeah, exactly. Just wondering, how does the memory controller here work? Like, I'm kind of wondering, is this expected to be just standalone, or was this be paired with some sort of processor as well?
I knew this question could come, so I have a backup slide on this. So there is a lot of details here, but basically you have a chip-to-chip link that is on the test chip. The test chip doesn't have a memory controller on it, okay? So every time you have memory access, you go through this chip-to-chip, you end up in a FPGA, and you use the FPGA interface to either DDR or HBM, okay? So you use the memory that is on the FPGA board to get your data. Okay. So in the case of the test chip that you saw in Antwerp, this is the behavior that we are using. In the case of the next tape out that we are going to have next year, we will have a LPDDR4 memory controller embedded into the chip. Okay. So that chip should be able to be a standalone chip booting without an external device.
So just a direct follow-up. This chip-to-chip is utilizing the Aurora IP core or the ZS interfaces, I guess, developed by...
This chip-to-chip is using the protocol underneath, I don't know. This is chip-to-chip by Xtol.
Okay, but it's serial communicate, high-speed communicate.
Yes, it's a SerDes, yes.
I'm thinking, like, let's say if a processor like RIA could also do some sort of maybe not stencil-based computing. Let's say just x plus y. In this case, would this still make sense for us to offload this to the accelerator?
So you see correctly the point, in the sense that right now, in a scheme like this one, the latency is very high, right? Because we have to go through this and so on. We have another implementation in which everything is on the FPGA. And here we have the opposite problem. The memory is too fast because it's so close and the core is so slow that, so that's the reason, because we did this short reason for long vectors. This is a document in which we analyze the effect of the latency to the memory that has 4 different codes that are sparse and dense. There you can find a little bit of the information that you are asking if you want to deep dive. In general, what we can say is that we don't worry too much about the latency, because once again, we have so much work to do when you have a vector instruction that basically the latency is keeping. So as long as you have data coming, you are happy, basically. Now, if you are thinking about the model, host device model, so we couple this with an ARM CPU, and we use it as an accelerator. Right now, we didn't explore much that model. Say we have an infrastructure that supports it, but it goes through Ethernet right now. So it's just a proof of concept. We cannot really measure things there.
So the chip itself would be still expected to work standalone, right? Like even if we integrate it into the task cluster, you would still expect it to be working on its own.
Now, are you talking about REA or are you talking about the RISC-V?
It's a RISC-V one, but since REA is sure to be integrated, I'm kind of wondering if this RISC-V chip also could make it.
No. That's why I was asking. So don't confuse. So this part is one chip, nothing to do with what I told today. This is called REA, and this is what has been announced that will be, I think, installed in one of the partition of the next generation system in Jülich. So it has nothing to do with this other chip. What it has to do is that in the ideal world, they should be like CPU, GPU, like host device model. But in the installation that will happen in Jülich, there will be only this part. Okay, so no RISC-V part. Yes, please.
So you can hide about 32 cycles of memory latency with execution, right? Or is there more opportunity for latency hiding? Because you have the previous instruction that maybe does something else that takes 32 cycles, and then you can just start the next memory instruction at the same time, but then you probably have a dependent instruction, or am I thinking wrong?
Well, imagine that we have several registers, right? So
okay, so you can
operate register 1, register 2, then register 3, register 4. And all this, in the meantime that you do all this, you can get data from the memory.
You need software pipelining for that.
Or like you can.
Yes. Of course, you have
put a few other arithmetic instructions that don't actually need the load, and then put the dependent. Okay, and that way you have multiples of 32, small multiples of 32, and that way you
probably yes.
Hundreds. Okay, yeah, I see.
Very follow-up question from what Dominic asked is, I think I didn't see it, but did you mention the cache line size?
Yes, because this guy is working at cache lines.
So how much cache lines are required to fetch the 16 KB vector registers?
64 bytes, one cache line.
64 bytes per cache line. Right?
Yes.
Why not make it as wide as the vector register? Probably bad for the scalar core.
If you do gathers top.
Yeah, that too. Yeah.
Yeah, I can imagine also from the routing and point of view, I don't know.
Yeah.
You have a jungle of wires there. Yes, please.
So the vector unit is it bypasses the L1, right?
Yes.
So can it do like memory gathers at all, like scattered memory access? Can it do that at all?
Yes.
Okay, and isn't the performance really bad when it doesn't go through the L1?
We are late, so yes. Okay. I mean, when you do gather and scatter, the performance are lower. So say unit strided, so contiguous is the best. Strided by a fixed value is worse, but is okay. And then you have the gather and scattered. So if you can avoid it, better to avoid it. Yeah.
It's the phase 1 and 8, I think, in the Alya code. I think those are scatters and scatters.
Yeah.
Okay.